the course of the next hour, I'm going to talk about how decomposing your application, how breaking up your monolithic web application has a number of benefits. You'll learn how it improves deployability and scalability. And we're also going to talk about how it simplifies the adoption of new technologies, how it makes it easier for your application architecture, namely that it improves deployability, it improves scalability of your application, and it also simplifies the adoption of new technologies. It allows your app to evolve. But before we get into that, just a little bit about me. So I actually grew up in England and then moved to the Bay Area, San Francisco Bay Area 23 years ago. I got my start in programming writing Lisp systems back in the late 80s. Lisp, of course, being one of those early dynamic, functional, and object-oriented languages. And then eventually I ended up in the world of Java, and about 8 years ago now, I wrote the book Pojo's in Action, which is all about how to build enterprise apps with Spring and Hibernate, which back then were these sort of radical new technologies, which today we pretty much take for granted. They've become de facto standards. And then I ended up in the world of cloud computing. Back in 2007, I started playing around with this obscure little thing called Amazon's Elastic Compute Cloud, and that evolved into an open source project, which then evolved into my startup Cloud Foundry, which was then acquired by SpringSource shortly before SpringSource was acquired by VMware. So that was back in 2009. And these days, I'm a developer advocate where I talk about Cloud Foundry and modern application architectures. So here's the agenda. So first, I'm going to begin by talking about the monolithic approach to building applications and some of the drawbacks of that approach. And then I'm going to describe how you can, by breaking up your application into a set of services, you could call it a service-oriented architecture, though that's sort of got a lot of negative connotations. You can actually improve many different aspects of your architecture. I'm going to spend a little bit of time talking about, well, what is a service? What does it look like? How do you deploy it? And then I'm going to finish up by describing the various options that you have to implement inter-service communication, REST and messaging, and talk about strategies for implementing robust, reliable communication mechanisms. Okay, so let's imagine that you're building an e-commerce application, an online store for selling products. Now, if you're like me, you'd probably come up with an architecture that looks something like this. You'd have the storefront UI, so that implements the presentation layer, the user interface. Then you'd have various back-end services. So you could have the accounting service that keeps track of customer credit. You'd have the inventory service that keeps track of where the products are in and out of stock. And then you'd also have the shipping service that would be responsible for shipping completed orders. So what's interesting is you'd actually have a logically modular architecture. But then when it came to deploy this application, you'd more likely than not package it up inside a WAR file and deploy it on a container like Tomcat. You know, you'd have MySQL or some other relational database in the back end. So we've gone from this logically modular architecture to, at runtime, this monolithic system. Now, on the one hand, having an architecture like this is good. It's simple to develop, test, and deploy. So, for example, when it's time to update production with a new version of the system, you just copy in that new WAR file and restart Tomcat, and you're good to go. And it's also pretty straightforward to scale. We can just run multiple copies of the application behind the load balancer. In this case, I'm using Apache, but you could use a real load balancer like a hardware load balancer like F5, for example. And you've got this nice scalable application. But there are, it's simple, but there are a number of problems with this monolithic architecture. So number one, over time, if you've got this large, complex system, it's just going to intimidate developers. They're going to have problems finding their way around the system just because there's just inside this monolithic system, which undoubtedly will have probably a complex build system, there's just all this code. It's going to be hard for new developers joining the team to actually figure out where to get started to fix a bug. And that's just going to lead to all kinds of problems over time. If people don't understand the system, enhancements and bug fixes won't get implemented correctly, and the quality of it is going to degrade over time. So that's a problem. Another problem with a large monolithic application is that it's a real obstacle to frequent deployments. In this day and age, we'd ideally want to be able to update production many times a day. But if you've got this large monolithic application, that means every time you push an update, you've actually got to update the entire system. So, for example, if you want to fix some text on a web page, then you're likely that you actually have to redeploy everything, the front end, the back end. That can interrupt long-running background jobs. If you're using Quartz, there's just this increased risk of something unexpected going wrong. And that leads to a sort of a downward cycle where people are afraid to push changes into production, which means that they do it less often, which means that it's actually more risky, which means that it's more scary, and so on. And so it really ends up being this just giant obstacle to frequent deployments, frequent iterations of your UI, for example. Another problem with a large monolithic application is that it overloads your IDE. The larger the application, the slower your IDE will be, the longer things are going to take, the less productive you are. It's also going to overload your container. It's going to overload Tomcat. So, for example, with a large monolithic application, it can take many minutes for even a relatively lightweight container like Tomcat to start up. So imagine you're fixing a bug. You make a change, you restart Tomcat, you wait a few minutes, that you haven't fixed the problem, and then you have to go around that whole loop many, many times. And if with a long startup time, that really slows you down. So the larger the application, the less productive you are. It's also an obstacle to scaling development. When you've got a large project, you really want to be able to split up the engineering team into sub-teams where each team works on a specific functional area. So you've got the UI team working on the storefront, where you've got the accounting team working on the accounting service, inventory team working on the inventory service, and so on. The trouble is, if at the end of the day, all of those changes have to go into the same WAR file, that actually requires a lot of communication and coordination between the various teams. So you could easily imagine a scenario where the UI team is ready to push their changes into production, but it turns out that the back end is not working because of some bug that was committed. And so there's a lot of back and forth and coordination and communication, and so teams can't work independently as much as they want to. And then another major problem with having this large monolithic architecture is that it really forces you into this sort of marriage with the technology choices that you made at the beginning of the project. New and better technologies come along every so often, and if you've got this monolithic application, it can actually be very difficult to incorporate these newer technologies. It's usually very unrealistic to do a complete rewrite of a system just so that you can use some much, much better framework. So as a result, you end up being stuck with whatever technology choices you made at the start of the project. So you end up with, technology becomes obsolete and no one wants to work on it, and it's sort of another downward spiral. Okay, so what can we do about it? So a few years ago, I read this great book, The Art of Scalability, which was written by some folks that worked at eBay and PayPal. So these were people who are used to working on large-scale systems. And not just large-scale systems, but also just kind of large-scale engineering operations as well. And so in this book, they present a really interesting model of scalability, a three-dimensional model, the scale cube. So along the x-axis, you have horizontal duplication, which is the kind of scaling that we're used to, where we're running multiple identical copies of the application behind a load balancer. And then on the z-axis, you have data partitioning, where, say, the primary key of a row determines which database server that row resides on, or perhaps some attribute of a request is used, such as the customer ID, is used to determine which server handles that particular request. So that's commonly known as sharding or data partitioning. And then, interestingly, on the y-axis, you have functional decomposition, which is where you break up the system into different parts by function. And really, the bulk of my talk today is about y-axis or functional decomposition. So if we apply that to our online store application, we go from this monolithic system that looks like this to a system that looks like that. So each of the modules of our application, at a high level at least, become their own freestanding application. So we've got the UI is its own standalone application, and then each of the back-end services is its own freestanding web application or program that has a main. And what this means is that each individual part of our system can be deployed and scaled independently of all of the other parts of the system. So we can actually apply x-axis cloning or z-axis partitioning to each service. There's various different strategies that we can use to partition up our system. We could partition by verb. So we have a service that's sort of responsible for implementing a particular use case. So that would give us something like the shipping service. We could also partition by noun, and we'd have a service that's responsible for all operations on an entity of a particular type. So that would give us something like the inventory service or product service. So those are the two main strategies for partitioning, by verb and by noun. And there's also some guidelines we could follow. So from OO design, there's a single responsibility principle that's an Uncle Bob principle from many years ago that says a class should only have one responsibility. It should only have one reason for change. We could apply the same thing to service design as well. A service should just have a single responsibility. We could also take inspiration from Unix, where Unix is comprised of a lot of utilities, cat, grep, find, each one of which just does one thing very well. And then, of course, you can write shell scripts that combine them together. And so this whole partitioning is somewhat of an art. You don't want to have too few services, because then we've got basically, instead of one monolith, we've just got several slightly smaller monoliths, so that's not good. And there's questions around, do we want to have, what happens if we have too many services? In SOA, there's this nano service anti-pattern. And there's always risks of having services that are too small. You've got the runtime overhead, for example, though hardware is relatively cheap. And there's always the potential risk of excessive network hops, where in order to handle a request, it has to bounce between systems, which can introduce excessive latency. And then there's always the risk of, if you've got this mesh of tiny little services, that, well, maybe that's difficult to understand. Though on the other hand, if they're reflecting the logical architecture of the system, then maybe it's not that difficult. So it's very much of an art coming up with the right number of services, and the answer really depends on your specific application and your specific use cases. So looking out there's a number of some really good real-world examples of organizations that have this architecture. So, for example, Netflix, video streaming service that in the U.S. is responsible for, I think, 30% of the internet traffic on some nights. they actually started off with a monolithic application, and then as they evolved, as they moved to the cloud, they embraced this service-oriented architecture. So Netflix today is comprised of many services running on this, globally distributed on EC2. Then Amazon, they actually started off in life with a monolithic application, and then as the online store became more complicated, they evolved into this service-oriented architecture. eBay underwent a similar evolution as well. So it's pretty common that once you start operating at scale, you need to adopt this architecture. And in fact, I heard that at Google I/O yesterday, one of the recommendations for running Java applications on Google App Engine was actually to do exactly this: break your Java app up into lots of small services with minimal class path dependencies. So even the Google App Engine folks are recommending this. So however, there are some drawbacks with this approach. Number one is complexity. The deployment time, we've now got all these moving pieces to actually monitor and manage and troubleshoot and so on. So there's definitely some issues there. Another problem is, well, if we've split up our system into multiple services, then we should have actually split up our databases as well, so that each service has its own database. It's not coupled to the database belonging to some other service. But then that gets into the interesting issue of, well, how do we implement a use case that would require a transaction that would normally span these separate databases? So we have to adopt different strategies. We probably have to adopt an eventual consistency approach for when it comes to transaction management. And then also, just if you're implementing a story or a use case that spans multiple services, actually rolling that out into production requires some careful planning. We can no longer just write the code, check it in, build the WAR, drop it into production. We've got multiple services that need to be updated in the right order. So there's some challenges there. And then there's also a challenge about, well, when do we use this approach? In the beginning of a project, imagine you're working for a startup. You don't have any customers. You don't have any scalability issues. And in fact, if you use this approach, then it will probably slow you down because of the additional complexity. So that's interesting. But then later on, once you've figured out your business model and you've scaled and you've got customers, and well, now we've got this monolithic application, but then we've got tangled dependencies because when we were building it, we weren't that entirely careful about managing dependencies within this monolith. Splitting it up into separate services can be a challenge. So there's some real interesting issues about when do you use this approach and how do you evolve from a monolith into a more modular application. But there's a whole host of benefits. It actually lets you scale development. Each service can be developed and deployed and scaled independently of the other. We can update the UI as often as we want without actually impacting the back end, which is great because we can run A/B tests and rapidly iterate on the UI. It actually simplifies distributed development and outsourcing. We've got well-defined interfaces between the components of our system. In fact, we could actually have components that contain items that contain that aren't of strategic importance to the company and ship them overseas and have them worked on by people outside of the company who don't actually have any access to the real crown jewels of our system. It improves fault isolation. If there's a memory leak in one service, it's not going to take down any of the other services, which is not the case with a monolithic application. And then, interestingly, it actually eliminates any long-term commitment to a single technology stack because there's no reason why different services can't be implemented using different languages or different frameworks. So it actually enables our application to evolve and adopt newer technologies as they become available. So we're sort of ending up moving from this sort of single language, single framework world, a monolithic world, into this modular, polyglot, multi-framework application world, which is incredibly exciting. So you can think of the architecture of your system as now having like two different levels. So we've got the system level architecture, which says, well, we have these services, they're going to communicate using these communication mechanisms, and that's the traditional, slowly evolving system architecture. But then each service has its own architecture. Provided it implements the right interface, the developers working on it are in theory free to pick whatever technology they see fit to solve that problem. So it really lets them pick the best tool for the job. And that at the service level, the architecture can rapidly evolve. If these services are small, there's no reason why you couldn't periodically just throw one away and rewrite it using a newer and better technology stack. You obviously don't want to have complete anarchy in your organization. You want to have some governance that restricts what languages people can use. But there's developers actually will have a lot more freedom to pick the technologies that are best suited to solving the problems that they have. And I think it lets the system adapt to changing requirements and better technologies without having to go through some, disastrous rewrite that sort of rarely works. And it also lets you, in theory, rather than just being a Java shop or a Ruby shop, lets you really just have this polyglot culture where you just go out and hire the best developers regardless of what languages they know. And now, since developers who know different languages tend to, each language has a particular way of solving problems, you end up with this very rich mixture of ideas, and it results in a much better culture. So I want to finish this section with a sort of thought-provoking idea. So you can think of the human body as a system. And what's really interesting about it is that every day, 50 to 70 billion billion of your cells die. Blood cells just last, a few hours. Bone cells last years. And actually, it's only brain cells that are with you your entire lifetime. Not even excessive alcohol consumption can kill them off. So there's this massive amount of cell death and replacement going on every day inside your body. Yet you, the system, remain you. So sort of an interesting challenge is, can we build software systems with these characteristics where bits of them are regularly getting torn down and replaced? And the famous computer scientist Richard Gabor has a great site, dreamsongs.com, where he has various articles and presentations on topics like this, very large-scale system design. It's very thought-provoking. Meanwhile, back in the real world, I kind of want to talk a little bit about developing and deploying services. So services in this new architecture come in all different shapes and sizes. Some of them can be web apps implemented with Spring MVC. You can also have just standalone apps that are not web apps. They just have a main, and they sit there processing messages on the message bus, receiving messages, publishing messages, making use of technologies like Spring integration. They might even be written in other languages as well. So, for example, some folks are building front-end servers using NodeJS. That's actually a particularly good way of pushing events to the browser. Maybe you've got some Ruby code in there as well. Here's a little standalone service that I wrote in Sinatra, and it just auto-responds to incoming SMS messages from Twilio. Then when it's time to deploy these services, you've got a variety of different options. Each service could run in its own virtual machine, or each service could run in a Linux container inside a virtual machine, or within a virtual machine you could have multiple JVMs with one service per JVM. Or if you really wanted to pack things in tightly, you could have within a single JVM multiple services. And you've got all these different options that really let you trade off isolation and manageability on the one hand, where if each service is in its own VM, then it's truly isolated from all of the other services and easier to manage. I should also add cost on here. It tends to be more expensive. Whereas if at the other end of the spectrum you've packed multiple services within one JVM, they're not really isolated from one another. Memory leaks would take down all of the services in that JVM, but you've got minimal overhead and also minimal cost as well. So you get to pick. There's a whole range of options there. And you could have obviously do this yourself, but in practice I found that using a platform as a service dramatically simplifies the deployment of your application. So obviously the one that I'm most familiar with is Cloud Foundry, and that offers some really interesting set of features. So for example, Cloud Foundry supports a variety of different runtimes. So Spring and Java and Grails, obviously Scala, anything on the JVM. You can also deploy Rails app, Node apps. And then the community's added support for languages like PHP, Python, .NET, and so on. And so if you've created this polyglot application that's written in a mixture of languages, it's very easy to run it on Cloud Foundry. Cloud Foundry also supports a variety of different platform services. So we've got database servers like NoSQL and Postgres, NoSQL databases like Redis and Mongo, and there's also RabbitMQ as a message broker. And then you have a choice of where you run it. You can go to cloudfoundry.com, you can go to a partner public cloud, you can run it in-house on your own infrastructure, and there's even a microcloud that you can run on your desktop. So you've got this great platform for deploying these modular polyglot applications. And there's various features that I think are really important. So number one is you get single-step deployment. With one command, VMC push, you can deploy a single application, a single WAR file, or you can, by writing a manifest, you can deploy many applications written in a variety of different languages. Cloud Foundry will go and create all of the required platform services, the databases, the message broker, and then deploy each one of your apps. And that's within just one command. You get access to all of these platform services. So you need a database instance, VMC create service will do that for you. And then you get simple scaling. You can adjust the number of instances of your app just by using the VMC instances command. +5 adds 5 instances, -3 removes 3 instances. And you also get automatic health monitoring and recovery. So if one of your instances crashes, it will get restarted. So just from looking at code that's been implemented, with using a PaaS compared with code that's written without it, there's sort of this benefits. You get this simplified and automated deployment that eliminates barriers to adding a new service, because deploying a new component in your application there's minimal friction to doing that. You don't have to talk to ops or anyone. You can just add it and deploy it. It also eliminates using a new kind of database. If it's available within Cloud Foundry, then there's zero friction to using it. There's no having to talk to operations about that. And then also, using a PaaS imposes a whole bunch of conventions on how you package and configure and deploy your application, which actually enforces consistency and just eliminates accidental complexity. It sort of takes away from you the ability to make arbitrary and unimportant choices about how you package and configure and deploy your apps. There's just one way, and that's good. It lets you focus on what's really important. Okay, so that's services. And now I just want to spend a bit of time, sort of final section of the talk, going over different inter-service communication options. So we've broken up our system into a lot of services. So whereas before, one service could call another, and that was just a simple Java method call, now we've built a distributed system, so we need some kind of inter-process communication mechanism. And there's lots and lots of choices. We could use HTTP, synchronous protocol, REST, etc., or we could use an asynchronous messaging protocol, JMS or AMQP. And then in terms of messaging formats, you get message formats, there's a lot of choices. You could use JSON, you could use XML. Text formats are nice because humans can read them. Or you could use a binary format like protocol buffers or thrift. So lots and lots of options out there. And you could say that there's sort of a preference these days towards building asynchronous message-based systems for reasons I'll go into in a minute. And JSON, of course, is today's popular format. It's human readable, readily consumed by browsers, which is obviously really important. But then on the other hand, a binary format is actually a lot more efficient. You don't have to parse it, parse the message, which is actually quite expensive. So, if we're looking at messaging, we could, if we applied that to this e-commerce application, we'd have a system that looked like this, where all the different components of the system communicate via a message broker, in this case, RabbitMQ. So you could imagine that when the user places an order, the storefront publishes a new order message via RabbitMQ. And then the back-end services will pick up the message, process it, generate new messages, and then eventually the order will be shipped. So, a number of benefits to this approach. It actually decouples the client, the producer of messages, from the consumer of the messages. The client doesn't actually have to know the URL of who's going to consume a message. It just has to talk to the message broker, which is then responsible for routing the message to the producer. So that simplifies configuration. And then another really critical feature is that the message broker buffers messages when the consumer of a message is down. So, for example, if the storefront will just keep publishing new order messages, and if the back-end services are actually down for whatever reason, the message broker will just buffer up those messages, and then when the back-end comes up, they will start processing those orders. So that means that regardless of what's going, the status of the back end, the front end can continue to take orders from the customer, which is extremely valuable. And then messaging is actually quite nice because it supports a variety of different communication patterns, not only point-to-point, but it also supports pub-sub, or you can make a request and then get a reply back later, sort of request-reaction type communication pattern. There are some downsides. You've got the additional complexity of a message broker, and also implementing request-reply style communication is a little bit more complicated. It's a little more roundabout, but technologies like Spring integration do simplify that. Another popular option, however, is to use REST, use HTTP REST, and you could also use SOAP, though that's sort of becoming falling out of fashion. And, in particular, I think REST is very good for communicating between the browser and your servers. So, modern applications tend to have an app that's written HTML5, JavaScript, running in the browser, and then the server simply exposes a RESTful API. There's a lot of pros and cons of REST. It's simple, familiar, request-reply is easy. It's obviously HTTP is very browser and firewall friendly. You don't need any intermediate message broker. There are some downsides, though. It only directly supports request-reply. The server, the recipient of the request, obviously has to be up and available in order for this to work. And then, interestingly, the client needs to know the URL of the server that it's talking to, which, on the one hand, just sounds like a trivial point. But then, when you're trying to implement a load balanced service, then you get into some very interesting issues where there's, in fact, multiple back-end servers, and well, how does the client know the URLs of all of them? I mean, you end up often having to have some kind of discovery mechanism there. So there's some sort of non-trivial subtleties there. Obviously, Spring Framework makes it very straightforward to implement RESTful APIs. Spring MVC is a very good technology for doing that. It lets you do URL matching and destructuring, so we can pull the account ID out of a REST-style URL. It also can automatically translate the object, the return value of a controller method into XML or JSON using message converters. So that just it's very simple, very direct. It can also convert the request body into from XML or JSON into a Java object and pass that as a parameter to your controller method. So all of the basics of implementing REST are very straightforward using Spring MVC. And then also there's another project that actually supports the so-called REST style known as hypertext as the engine of application state, which has this hideous acronym HATEOAS. And the idea here is that a REST API only has one known URL, and then the application has to discover the other URLs for acting on resources by following links that are embedded inside these resource documents that you get back. And don't really have time to go into this, except that if you Google Martin Fowler, Richardson, no relation maturity model, you'll find a very good write-up on the various different kinds of REST and how this is considered the sort of nirvana of REST. And so there's a Spring project, Spring HATEOAS, that makes it straightforward to build this style of RESTful API, and I'd encourage you to have a look at that. Obviously, in Spring, there's the REST template that makes it straightforward to consume RESTful web services. And then, interestingly, there's also the Spring REST shell that's this command line that gives you this shell that lets you navigate through and make requests on HATEOAS-style RESTful APIs. And I encourage you to go check that out. You can it's like equivalent of CDing and LSing around a file system, except that it's really a RESTful API. Okay, so that's sort of the basics of communication. You've got choices, messaging or HTTP, REST, etc. Spring is very good for doing both of those. I want to talk a little bit about the need for parallelism. So imagine that once again you're implementing this online store and you're writing the controller method that has to render the page, or at least get the data to render a product details page. Now, if in this service-oriented architecture, you're probably going to have the product details stored and provided by one service, the recommendations stored in another, and the reviews stored in a third. In fact, there could be many, many more. So, a request comes in to get for a particular product details page. You need to call all of these services. You could call them sequentially, but that would result in sort of terrible response time. And so you actually need to call them in parallel. So that means that we need some kind of concurrency mechanism in our code to actually make multiple requests in parallel to all of these different back-end services. Obviously, we could just spin off threads and do things that way, but that's sort of tricky and error-prone. And so what I found is that futures are a really, really good concurrency abstraction that make writing this kind of code a lot easier. So, what is a future? So it's an object that will contain the result of a concurrent computation. So you can think of it as a little box. So the caller initiates an asynchronous operation. They get a future in their hand, and off in the background, that asynchronous operation is being performed either by using threads or using some kind of asynchronous callback style approach. And then eventually the result of that concurrent operation is then put into the future. And then the client can get the value out of that future. So obviously Java has that in the form of, it has a future implementation, and you've got the executor service that when you submit a callable, it will give you back a future. And it turns out that Java futures as in JDK or Java 7 futures are actually really basic, and there's much better implementations out there. So, for example, the Guava framework and also the forthcoming Java 8 and also Scala futures let you attach callbacks. So rather than you having to keep polling the future or blocking to get the value, you can attach a callback, and when the value arrives in that future, you will get notified via a callback. And that makes it a lot easier to write asynchronous code. And then an even better mechanism that some future implementations such as Scala provide is this whole composable futures. So you can create futures, you can apply a map operation to them that actually that gives you back a new future, in this case containing the original value times 2. You can combine futures, and then you can do some interesting transformations, like transform a list of futures into a future containing a list of their values. And Java even has syntax that makes it very straightforward to write concurrent code, either for comprehension. So here we're actually having two operations execute in parallel, get their results, and then invoke a third concurrent operation with their values B and C. That gives us back yet another future, and then we can eventually wait for the return value. So I'm kind of skipping over the details, but I'd encourage you to go have a look at these different future implementations, and also the recently announced Reactor project that's also from Spring Source. That's actually got a future implementation as well that's looking quite good. Obviously, Spring integrations, another key technology that one could use here. If you're building a message-oriented system, it's providing all of the big building blocks that you can wire together declaratively to build a messaging pipeline. And then sort of the final main topic here is, well, now that we've built a distributed system, we have this whole problem of partial failures. So before, when service A called service B in a monolithic application, that was a Java call, and there were no subtle issues around that. But now, service B is in another process, and it could be down or it could be slow. Or the network that's connecting the two could be down or could be slow. So we've got this scenario where bits of our system are working, but other bits are slow or completely down. So you actually have to design your system very carefully to avoid a whole bunch of problems. So great example of that is Netflix, once again, the video streaming service. And they're operating at this massive scale. They're actually processing more than 1 billion API calls a day. And each API call actually fans out to 6 back-end service calls. So that's 6 billion calls every day. And you can imagine, fault tolerance is absolutely essential when you're operating at this scale. And they published a fascinating series of blog posts on techblog.netflix.com that describe the mechanisms that they use to build a fault-tolerant, robust system. So the problem they're really trying to solve is this. So imagine a request comes in, gets allocated to an execute thread, service A is invoked, so that's all within one JVM. But then service A invokes service B. So imagine service B is down and doesn't respond. So that really means that service A is, without doing, if you didn't, will just end up being blocked. And that will kind of tie up that one execute thread, in theory, indefinitely. another request comes in to do the same thing, it's going to get blocked. And then, then another request. And before long, maybe you've got a few hundred threads inside your Tomcat server, and if requests are coming in, many times a second, you're going to very quickly run out of execute threads inside your Tomcat server, which is basically non-responsive at that point. And that could happen across your entire site within just a matter of minutes. And so, one service that if you call a service that's down and you block indefinitely, all of your execute threads across all of your servers will actually be busy, will be tied up, and your site will be down. So what do they do about it? Well, they sort of have a number of different ways of addressing this problem. So number one is whenever they make a request over the network, they never block indefinitely. They always time out. So the scenario that I described will not actually occur. And then if some error does happen, they're most likely retry, because often sort of you get these transient errors in your system. So number one, though, is you just never, you always time out requests. Another problem, another strategy they use is that they always invoke a remote service via a bounded thread pool. So in other words, when service A calls service B, the application code doesn't do that directly. Instead, it submits a callable into a bounded thread pool, and then the callable makes the request to B. And that has a number of benefits. Number one, it actually limits the number of outstanding requests. Because the thread pool is bounded in size, there can only be some finite number of outstanding requests from A to B. And then also, because the queue that's attached to the thread pool is bounded as well, if B was ever down, the thread pool would fill up, the queue would fill up, and then you'd start to fail fast. You'd have execution rejected exceptions. So no one will ever you never wait indefinitely to execute the callable to make the request to B. And then they also use the circuit breaker pattern. And the idea here is that if the circuit breaker sees a number of requests to B fail, it will actually, the circuit breaker trips, and any subsequent, for a certain amount of time, any attempts to call B will actually fail immediately. So that has the advantage of, well, if B is down and is unresponsive, we're going to fail straight away. And it also gives B a chance to recover. So maybe B is just overloaded by having the clients temporarily sort of back off and not actually make any requests. We're giving B a chance to recover. So that's another really critical pattern. So by using a sort of combination of these approaches, you end up with very robust inter-service communication. Now, obviously, if there is a failure, well, what can you do? Well, one option is rather than just failing back to your caller, you actually return default or cache data. Great example of that is if you're, you've called a recommendation service and the recommendation service is not available, you still want to return display the product page. So in this case, the default data is null. Or maybe there's nothing you can do and you return all the way back to the client, and then the client can decide whether to display a message saying, sorry, we can't play this movie, or maybe the client will just repeat the request, get load balanced to an entirely different set of servers, and the request will be completed successfully. So you've got various different strategies on how to recover from error. And they've got a library, Hystrix, on GitHub that implements many of these features like the circuit breaker pattern. Okay, so that's pretty much my talk. So in summary, monolithic applications are simple to develop and deploy, but at scale they have significant drawbacks. So you want to apply the scale cube and decompose your application And that lets you develop and deploy all of these services independently. And of course, the services might be written using a variety of different languages and different frameworks. And then having a platform as a service like Cloud Foundry can simplify the deployment, development, testing of those applications. So thanks for listening, and hope you found it useful. And we have a little bit of time for questions.
Excellent, Chris. Thank you very much. Yes, so folks, please feel free to use the question and answer panel in the WebEx to ask your questions. We had a couple that I attempted to answer, and I'll give you a crack at them anyway because we don't have a huge amount of questions, so that's I think we have time to kind of go through and address everything. So, Chris, one of the questions was, do tools like JRebel allow people to avoid deployment overhead? And I clarified a little bit, and I believe he's referring to LiveRebel. This question comes from Dennis.
Oh, yeah. I mean, that's interesting. I mean, I haven't actually tried to use those tools, but I'm guessing so LiveRebel lets you update production and without. To me it sounds kind of appealing, but I find that based on my experiences, running say the original CloudFoundry.com, it's like deploying application, updating production is this scary, stressful experience. And if you can just, and there's always, you always get surprised. And so if you can actually, rather than having one large, complex, monolithic system, if you're, say, working on the front end, know that you can just update that and know that nothing that's going on in the back end will ever be touched by that change. Or say if you're working on the registration component, knowing that you're just going to touch registration and you're going to leave actual provisioning of VMs unaltered, I think that just makes things a lot, much more, much easier, much less stressful. It removes that element of fear, which ends up being a giant obstacle to updating your systems frequently.
Thanks. Yes. And he did go on to clarify, I've had some experience with JRebel, and as far as I know, it's like this helps you, dynamically sort of avoid redeploys, right? It's like you can just file save a Java class and it's live. But
I know people who have had a lot of. Sorry.
No, it's okay. I don't see how that would help you decompose a system. But so if you want to clarify your question a little bit, or maybe give us via the WebEx panel, and maybe give us more of a sense of what LiveRebel does that maybe we're unfamiliar with, please feel free, and we'll try to respond to that. In the meantime, I think I'll move on to the next question. And that comes from Joao Luge. And he says, by partitioning applications, we'll need to solve user management. Yes, that can also be a service. But what is the best practice for user management? I think what he means by that is that the authenticated user interactions that span several services will need to know what user is interacting with them.
Yeah, effectively you're in this, it's basically we're in this kind of a single sign-on scenario where, you've got to have, when, say, different components, that one service calls another, the user credentials, some kind of token is going to have to flow along with those requests.
And is that the kind of thing, Chris, that you would see, is that the job of a cookie, or is this more of like an OAuth kind of thing, or, like a SAML kind of thing, or roll your own?
Certainly, some of it is cookies, say the front end. Yeah, the front end can like you could have a front-end server that's handling the authentication, and then so that's sort of fairly normal, and then it just has to pass some user identifier when it calls forwards of, say, an HTTP request to the back end, and that could be a cookie, or I guess there's various different ways of specifying the user identity in the request, but cookie is one option.
Okay. This is an interesting one. I had a question from a gentleman named Abhishek Roy, and he brings up the topic of OSGI, and he has a disclaimer here saying he tried it a couple of years back, but he had a tough time actually getting OSGI-ified, jar files, and he doesn't ask a question per se, but I can kind of see where he's going with this.
Yeah. Well, I have a few thoughts. It's kind of interesting because OSGI, to some extent, is a technology designed to solve problems with large monolithic systems. In a sense that, in being able to independently redeploy OSGI bundles. So if you actually break up your system into smaller services, that problem goes away, and you don't need OSGI. That's my general answer, which I think is quite good because OSGI is, to me, hideously complicated and not very developer friendly. So if you can avoid using it, that's a good thing. I did talk with someone who was using OSGI to enforce very rigid rigid distinctions between public and private interfaces, which was an interesting argument. Though I suspect, once again, there are other ways of stopping your developers from bypassing APIs and going and digging into the internals. But then having said that, I did hear of one company who was operating at such humongous scale that they wanted to run multiple services inside one JVM. And in order to do that, in order to get true sort of isolation and independent class paths, they were actually using OSGI to do that. But this was a company that I think was operating at such extreme scale that they needed this very densely packed infrastructure, whereas most people don't have that problem.
Cool. Okay. Thanks, Chris. Let's see. Wow. Okay. Getting a couple more questions come in on the panel too. Hopefully, do you mind going a little bit over time, Chris? Is that all right?
Oh yeah. Gosh,
okay.
I'm fine.
Excellent. Wonderful. Okay. I'm sure they'll appreciate it. So let's see. Next question. Hang on just a second. I lost my place. There we go. Okay. I'm not entirely sure what Julian Huller is asking here, but he says, "Hi, is the RabbitMQ share its behavior to a UDDI for web service-based services?" I think what he's saying is, can RabbitMQ somehow register itself in the directory? Julian, if you're still on the line, you want to clarify, please feel free. But Chris, I think that's what he's asking.
Yeah, UDDI. That was the whole SOAP thing, right? I'm not sure what he's getting at there.
Well, since you've been talking about REST pretty exclusively, I'm guessing that I don't think UDDI has evolved to the point where it is a registry for REST services.
Right.
So I'm guessing that it's just sort of orthogonal in that, I don't know, maybe RabbitMQ coincidentally does have some sort of SOAP interface, but think you're talking about REST, and I think REST and UDDI don't play well together.
And then when you say Rabbit, then I think of messaging and UDDI don't play well either.
Okay. All right. So, Julian, let us know if we answered your question there. That may not have been the answer you wanted to hear, but
I mean, I should say, my email address is up on the screen, so happily we'll have offline discussions with people as well.
Yeah, thanks for that, Chris. That's kind of you. Okay, excellent. So Dennis asking the question on the user management before follows up with some additional questions. In case the application is separated into different wars, how do you support one HTTP session for all services? He goes on to clarify, how do you avoid the performance impact when you have to pass data objects from one service to another service? As Chris, as you pointed out in the presentation, converting to from JSON XML can be expensive. You have to parse it, blah, blah, blah. Would distributed cache be a solution there?
Yeah. Okay, so, one part of it was session management. And in general, having stateless servers is a good thing. So as in like stateless application servers, especially in a cloud environment where you might want to auto scale up and down, at will. And so common pattern there is actually to have the session state externalized and stored in some data store. So one example of doing that is using Redis as the session cache, that high-speed in-memory key value store that's like ideally, super fast, ideally suited to storing session state. So you end up with just, you've got front-end servers that are storing session state, but then that's just this really stored off in Redis. So that's one part of it. And I guess I think, say, the overhead of passing data around is maybe that's limited to like super high volume systems where you're processing large numbers of messages every second. I don't know if it would really be significant in sort of the typical system. I think lots of folks are just happily using JSON for the format for their requests. And I remember encountering people who were doing these high volume systems, and that's when they switched to a binary format. But I think for the most part, it's not a major issue.
Thanks for that, Chris. And do you see distributed caching, in-memory data grid type technology as a solution potentially there, as a way of kind of having an external, coordination layer?
Yeah, I think in general, just in general in systems architectures, just having a in-memory grid in front of your not so scalable backend or backend databases or mainframes or whatever it is you have. So, is generally a good thing, and that could, that I think that does improve performance and scalability.
Cool. Okay. Thanks for that. And a question from David V. How can I communicate between two wars deployed in the same virtual machine? Something like JMS or EJBs, for example. Would those be good solutions?
Yeah, I look at two wars as really being two services, and so, that goes back to, well, what are the communication options? So one of, it's either, it boils down to HTTP or messaging. Or, I suppose strictly speaking, there are other protocols, but just pick one of your standard communication mechanisms.
Yeah, messaging was the first thing that popped into my head when I saw that too.
Yeah.
Yeah. Okay. Next question from, please forgive me for mispronouncing your name, Mehdi Zabaton. He said, hey, thanks for a nice presentation. Imagine we have some war applications that should communicate in the service layer. Is it good to use REST? What about transactions? So I think you answered is it good to use REST, but I think really what he's after is what about transactions?
Yeah, I mean, transactions, you end up having to design your system in a different kind of way where so for example, let's sort of pick a good example. So like imagine you've got customers and orders, right? So you could have a customer service that's got a database of customer info, and then you've got the order management service that's managing orders. But interestingly, orders sort of need to know about customers. So what you'd end up doing in this case would say in the order management service, you'd actually have a customer table that would have a stripped down, would have a subset of the columns from the main customer table, customer name and address, say, as opposed to tons and tons of details about customers and their cool history and CRM type stuff that might actually be in the customer database. But that in this kind of system where it's like, oh, well, we need to change the customer's phone number, or maybe the customer changes their address, right? I mean, companies move, for example. So then that change would actually happen inside the customer service, and the change would be made in that database. And then probably, one strategy would be to then send a message to the order management service saying, this customer has this new address. And then eventually the order management service would then process that message and update its copy of the customer. So we're ending up in this world of eventual consistency where databases aren't consistent all of the time. They eventually become consistent as the changes propagate through your system. And basically, any sort of transaction management that would otherwise span multiple databases has to be implemented using a mechanism like this, like change it in one database, send a message to change it in another database.
Sorry about that, Chris. I was just on mute for a moment there. Okay, great. And thank you for that. And then we've got a couple of other questions, so I'm going to pick up a little more speed, okay?
All right.
Okay. And then hopefully let's see, we've got like 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. Upgrading services in an active system often creates versioning issues. Can you discuss technologies or patterns or approaches for handling that? This comes from Arden Klein. Excellent question.
Yeah. One simple change is, well, we're just, if you think of a service as having an interface and an implementation, right? Changing the implementation, that's sort of a no-brainer in the sense you just push changes into production and the clients don't know any different. You could change the interface by adding new, quote, methods to it. And that once again, that's a harmless change, right? You can roll that change out into production without any problem. A more interesting scenario is one where you've changed the interface incompatibly for whatever reason. And there, one strategy is you say you had version 1, it's running, and you just deploy version 2, and they could basically be running side by side. Obviously there's issues at the data. They have to share the same database because logically they are. and then so you roll out version 2 with the new API. This goes back to a slide I had earlier where you're implementing a story that spans multiple services, and it's kind of like you have to roll out the bottommost service first, and then you'd then have to roll out the clients. Then you'd update the clients of that service so that they would use version 1 instead of version 2. And then if they have clients, you'd roll out their, the client of the client. So you gradually work your way up the dependency tree, rolling out updates. And I think that's a strategy. I mean, it requires some careful planning, but I mean that's a strategy to use.
Thanks for that, Chris. Okay, let's see. Another question. Let's see. Hold on one second. I see. Another question from the same guy, Mehdi Zebeton. Imagine service A wants to join data with service B, or in database or JPA. Is it simple to use some sort of a database join, right? But if service A is in one application and service B is in another, what's a good pattern to join data?
Yeah, this is a really interesting issue. I mean, obviously, one option is you could do some kind of join at the application level, which might be horrible. I guess this sort of gets into the issue of, well, if there are things that you need to do that actually span multiple services that in this partitioned architecture are inefficient, then there's a whole question about, well, is your partitioning correct? Perhaps you should not, if you've got these operations that really are spanning multiple services and are hence quite expensive to implement, then well, maybe you shouldn't have partitioned your system up that way.
Yeah, good point.
Yeah. Or the other option is you just constantly replicate data from one system to the other so that the other system has the data that it needs to join against. I mean, there are strategies. I mean, there are strategies, but yeah, I mean, it's like you don't want to partition your system in a way that creates problems.
Yeah, that sounds like a design issue from the start.
Yeah,
I agree with you. Next question is from Shashi Ranjan. Hi, I have an application where it has many modules, and we've made the service layer independent, and management of services has become easy, but we're still forced to use a single WAR for the front-end UI. Is there any way to modularize and split it module-wise?
Yeah, that's a really interesting issue. I was thinking about that the other day. I'd actually imagined, like, okay, you have a user, like, take a stock trading application, right, where you've got various screens like overview, trading, transfers, and so on. I mean, I think in theory, each one of those could actually be a separate standalone. I mean, because I'm thinking about like HTML5 or JavaScript apps, and I'm thinking that each one of those could just be its own standalone app. And then, so when you navigate from one section of your site to another, you're actually visiting an entirely different page and an entirely different standalone app. So I think it's doable to split up your UI.
Thanks for that, Chris. Yeah, I know. I know some of the other architecture that we at Spring Source have been talking about lately has been, possibly sort of moving the model view and the controller into the model view controller layer off the server and onto the client with JavaScript. I wonder if that's another way to.
Yeah, I mean that's what. Oh,
out.
yeah. Just to clarify, I mean that's the kind of apps that I'm thinking about these days. Like I mean, in my mind, I mean the right way to build apps today is, model view controller resides in the browser. You're writing in JavaScript or some similar language, an HTML. Whether that's like Backbone or Angular JS or Knockout JS or pick your favorite browser JavaScript MVC framework, and then you're communicating with the Java applications are just exposing RESTful APIs that the browser then consumes. But then the interesting thing is you do it. If you just did it naively, you'd end up with a monolithic browser app, which is perhaps not what you want. But then I'm thinking, well, we can just partition up the front end so different functional areas of your user interface are actually different standalone single page browser applications. And when you navigate from one functional area of your UI to another, you are actually loading in a fresh new page than a fresh new MVC app. So when you go from portfolio overview to stock trading, that's a different. Those are two different single page MVC apps in the browser.
Excellent, thank you. I think we're going to wind up the Q&A here. We've got a couple more in the stack. Just because a number of people, I'm going to skip one or two things. Two kind of related questions, one from Philip, another guy named Philip, and another one from Robert, both asking about like inter-process communication, right? Philip asked what binary format you recommend for inter-service communication. Robert asks, what about Spring remoting? Do you recommend it as a protocol for inter-service communication? All kind of revolving around the same theme here, right?
Yeah, I mean, this Spring remoting, I mean, that makes it's very, very easy to just get up and running with Spring remoting, right? It's just, a few lines of HTML, a few lines of XML in the client, few lines of XML config in the server, and you've got communication. And so, so that, I think it's like if you're living entirely within the Spring world, then of Java JVM world, then yeah, you can by all means leverage those technologies. I mean, it gets more interesting if you've got a mixture of languages, and then like you need a portable communication mechanism, and then that pushes you in the direction of like REST or JSON formats and so on. I mean, I don't have a specific binary format that I recommend. I mean, there's just a few out there, right? Like Google protocol buffers seems kind of popular, and there's like Thrift and Avro, and I forget the names of some other ones, but I think that they're worth looking at.
Excellent. I think there's only three more questions, but I'm starting to run out of time too. I think maybe we have time for one last one.
Yeah, and if you've got unanswered questions, once again, please shoot me an email, and I will do my best to answer it in a timely way. Thanks for that.
And I just do want to mention that there's some interesting new JavaScript libraries out from SpringSource. If you look at the Cujo.js project, that also can help with modularity and module loading and concatenation and that sort of thing.
That's great. I mean, you get dependency injection for JavaScript apps. Fantastic stuff.
And that, while that isn't a silver bullet for not creating, decomposed JavaScript applications, that are doing the MVC on the client side, it can certainly help quite a bit. So if you may want to check that out. Again, just Cujo.js. Take a look at that. You can find a GitHub repo with a simple Google search. Fam asks, how do you resolve the security issues between services that are implemented in different technologies and protocols?
Yeah, I mean, that's an interesting one. I mean, it's sort of the upshot is, right, is you end up just having to use a variety of different yet equivalent frameworks, one per language, one per technology, for dealing with things like security and sort of other it's kind of like all of these cross-cutting concerns, right? You want every service needs to do logging, you want to do authentication, so on. And yeah, if you've got one service written in Java, then you're going to use Java libraries to do that. Whereas if it's written in Ruby, then yes, you've now got to use the Ruby equivalents of the same thing. So things do get a little bit more complicated. Because you end up having different ways of achieving this, of implementing the same cross-cutting concern, but there's no other way around it, really.
Okay, folks, I think we're going to have to wrap it up. Thank you so much for all the interactivity. Really appreciate it. And we'll have a recording of this webinar posted on our YouTube channel, SpringSource.dev. youtube.com/SpringSourceDev. We try to have that up at the max of about 2 weeks out from the date of the webinar. Often we have it up a heck of a lot sooner than that. And you can be sure that we monitor the questions sometimes on those YouTube videos. But Chris was kind enough to offer his email directly to you, the attendees. So please feel free to interact with us in any way that you feel called to. And also, we have another upcoming webinar a little bit later this month. Obviously, we'll be publishing the June webinar schedule fairly soon as well. So if you're interested in some more good content from developer content, on May 28th, we have lessons learned moving from Google Web Toolkit to Spring MVC with a speaker from Broadleaf Technologies, Andre Azzolini. So please join us for that if you'd like, and really appreciate your time, your attention, your questions, and hope to see you on a webinar again very soon. Thanks so much, everyone.
Thank you.